Good afternoon, everyone. It's 2:30 p.m., so let's get started with this afternoon session. My name is Jerry Haan from CERIAS, and I'm delighted to host this afternoon session of the Faculty Tech Talks. We have two great talks this afternoon from a couple of very popular faculty members, so I think you'll enjoy both of these talks today. Our first speaker is Professor Aniket. He's an associate professor in computer science at Purdue University. He is an applied cryptographer and a privacy researcher. His research builds on and expands applied cryptography, distributed computing, and data-driven analysis to solve security privacy problems in decentralized environments. His current projects focus on communications freedom in distributed ledgers, or blockchains. He is a recipient of the NSF Career Award in 2019. Before joining Purdue in 2015, he was a junior faculty member at Saarland University, Germany. He completed his postdoctoral fellowship at the Max Planck Institute for Software Systems in Germany. He also received his PhD from the University of Waterloo, Canada, and his master's from IIT Bombay in India. So with that, let's start Professor Kate's presentation.
Hello, everybody. My name is Aniket. I'm an associate professor in the computer science department at Purdue and affiliated with CERIAS. Today, I'm going to present you optimized distributed analytics for dynamic cyber physical systems and Internet of Things. Our aim is to remove the need of a centralized aggregator, as I'm going to explain in this presentation. This is a joint work with my collaborators, Professor Bakshi and Professor Reicher, and as well as most of the interesting work in this, that we are doing is performed by our students who are working in this field. This work was initially supported by a CERIAS seed grant and is currently supported by AR. So we are talking about CPS and IoT. When we look at the CPS and IoT in general, there is no need to tell, for me to tell this audience the importance of that indeed we are seeing an increasingly important role that CPS and IoT that are playing in our environment. In particular, what we see is that they are getting used in our homes to actually manage our temperatures or manage our refrigerator stocks or manage access control, air quality, all these examples. They are getting used in agriculture for soil management, pest control, see how herds are moving, managing the herds as well as managing their health in this environment. And all the way to even medical environment where they may provide critical assistance with the tracking information, monitoring patients in the hospital as well as in their homes and whatnot. There are several significant advantages for CPS and IoT that we can also add into. However, if you look at the current typical approach that is associated for all sort of data gathering, analysis, and analytics in general for the CPS and IoT, they follow what is known as hub approach. So by hub approach, what I mean is that consider this setting in a home where there are different IoT devices associated, let's say, starting from alarm clock to the refrigerator. And they are actually working in sync. It's not that they're working separate. And the way they typically are working together is that they are sending this information to the gateway or router that's present in the home, and possibly then they work combined in a manner so that they can actually perform synchronized actions and meaningful action and actually assist each other via some kind of analytics that's happening in an IoT CPS hub. But the aim here is this hub approach. Typically, everything is collected from these devices, which works just as a data collector, and possibly somebody who is going to get response or the actions from the hub via gateway and then perform those actions. However, maybe this is fine for the home environment and also for some other environment, but not in all environments. In particular, there could be environments where we are using CPS and IoT where we do not have available such a hub 24/7. Access to such hub or such a either to such a hub or those hubs themselves could be intermittent, ad hoc, maybe just works every now and then. It can be also a situation that the communication links from those devices to the hub can be expensive in terms of the energy that they require. And those devices that are running, the IoT and CPS devices that are running, may not have access to some continuous energy resource, so that then they may drain out energy to communicate all their information continuously to such a hub. In general, also one more thing that can happen in such in all such environment is that because we are collecting information, sending that via gateway to the hub, and then hub is supposed to work on that, send back the answer, there is the inherent delay. So what it typically does not allow is any performing any kind of real-time analysis. Real-time analytics, for example, could be scenario where multiple sensors see some event and they take action immediately without actually consulting such a centralized service. They communicate with each other, make a decision, and execute such a. Example in home could be that there is a fire and the sensor detected that and they actually start pouring water all over the house so that the wire is fixed. That could be an example for that. But indeed, you can envision quite a lot of examples. So in general, what we do in this work is we question such a hub or such a centralized access. You see that in the environment where it is necessary that we do not have continuous access to such a centralized aggregator of the information, or access to such centralized aggregator are also expensive, and where we indeed demand real-time analytics, where we do not have time to go through such a centralized server, which could be far, and get back the answers, can we do and solve interesting problems and perform real-time analytics just within the CPS environment? And to explain that, I'm going to take a couple of examples. My first example is associated with the battle. And what I'm showing here is a kind of three-tiered architecture. So what I'm assuming is that there are low-level event generators and other devices which are actually in the battlefield. Several of them could be communicating with each other by themselves, and they may want to make sure that they work in a synchronized, coherent fashion. Talking from the very simple perspective, they want to make sure that their actions are not conflicting with each other, and that they send each other correct and meaningful data. So, and then they could be themselves talking to some middle level computers, which could be just some kind of a drones or the better devices that are running. But again, they may be intermittent. They may not have direct and continuous connectivity with the devices on the ground. And but they themselves may be dynamically moving and talking to each other when possible over the partially connected network, and trying to make some kind of agreement again of the process and taking agreed actions in a coherent fashion. While there could be a top level validation, as we are showing here, where the idea will be which will collect information from such second level, middle level, or a low level node. But the important thing which can be associated with such top level devices or command and control, as we can call them, that they may be even less available to the lower level devices, and to a lesser extent also to the middle level devices. So the aim for a real-time provenance, a real-time analytics, is to make sure that whatever decisions we can make on ground, we make those on ground. If we cannot make those decisions on ground because of insufficiency of the information or possible compromise of the information or some jamming or some events where the communication links are got destroyed, there we could include in principle the middle level to get involved in that. And decisions are made now with the help of the middle level or at the middle level. And only when things are going really bad, where say the infrastructure is severely compromised, and that there are basically partitions of the network that are happening at the lower level, then some kind of a top level domain that comes in such environment. So what we want to do is that we want to build solutions where indeed we can perform such actions and perform such agreement on the actions across these different layers. So again, as you already mentioned, these different layers are connected to ad hoc wireless means. We can still make sure that when some things are not possible at a particular level, that then because of the some insufficiency of the information or insufficiency of the communication links, then we should be able to offload those decisions, that computation to the next class in particular, and then get back the answer from the class and perform the actions. And but at the same time, we have to also make sure that there can be uncertainty at every layer. What could be important challenge and problem to associate that, to determine this uncertainty at those levels. Once we figure out that there is indeed uncertainty at this level, figure out the algorithms and protocols, deal with them, and only when we cannot deal with them at that level, then involve the next layer or the layer above, which may have better protection, and that's the reason can be difficult for adversary to control. So in general, what we want to make sure that we perform analytics just at these individual levels. Actually, I'm going to change the domain and give another example now, demonstrating it's not only that the battlefield where it could be. And my example is associated with the farming, and a term that typically gets spoken quite a lot in this exam, in this word, is the precision agriculture. We want to make sure that when we are in the crops, we want to make sure that we monitor the soil for the nutrition, for the pesticides and chemicals which are present over there, and how is there some kind of action that we need to perform or possibly penalize the farmers who are not following the practices that are suggested by the authorities over there. Or there could be examples where their livestock and that livestock is roaming over all big areas, and in such an environment we want to keep track of those livestock as they roam around, possibly determine their health condition as early as possible, and then so that we can indeed, based on them, make decisions associated with what to do and what should be the use of those livestock according to their health information that we are getting. In all these examples, we can expect that the farms or such infrastructures have sensors of different kinds which are present there, which in principle can be collecting data. In terms of the soil monitoring, it could be just some sensors in the land which look at the different levels of the different chemicals in the sand and try to make decisions about that. And there could be drones which regularly reach there and try to collect data from there and bring back that data to some centralized place where we do analysis about them and figure out what kind of action that we need to perform there. On the other hand, when we consider livestock monitoring, we could be placing very small sensors on each of the livestock, and then idea could be we have some kind of gateways or drones which could be flying and try to collect this information from there and then perform actions on the top and based on those. So I'd like to indeed mention that why still this is a challenge. I mean, the challenge comes from the scenario indeed that where things can go wrong very fast. Let me take as an example this scenario given the soil nutrition model. Okay, there could be easily scenarios where the farmers have benefit to obscure the information that is collected from their farm because that could be associated with the toxicity of their soil and could affect the farms, and the price of their crop will be dependent upon that. They may want to actually tamper with the data that is provided by the sensors in their field. They may also want to possibly destroy the communication so that the other farmers get penalized in incorrect fashion, or that they gain benefit from that because of the information from other farmers. So as they're showing in this particular picture, there could be adversary which is sitting at those different sensors, which are the owners of those farms, as well as there could be adversary who may try to actually jam the communication which is going from the legitimate nodes to the tools which are collecting the information. So another aspect that I already mentioned is this is one particular scenario that these drones may be very infrequently visiting such sites and maybe can collect data only infrequently, maybe once in a week, once in a month in such an environment. However, these sensors are continuously collecting the data. Now, given such an environment, can we do something interesting so that these sensors themselves do analytics and come across some kind of agreement on the soil level in the environment and make decisions on based on that possibly uh, uh, not rather than just collecting individually data and just pushing that to the drones. If they can do some kind of analytics, that could be really beneficial for such environment. So the idea could be the nodes in real time communicate with each other and perform consensus and agreement on the values that they got. And when the drones come by, infrequently they can offer only an aggregate information back to them, which could be energy efficient for them and could be sufficient for drones to further perform the action, which may not require the huge payload to be uploaded to those drone nodes that is collected over the weeks or months. The advantage of this could be if these analytics are functioning correctly, then drones can reduce the frequency with which they have to visit the farms to look at all these. So I will like to mention here, I'm already using word consensus, and won't you just say, wait a second, okay, we can assume that these nodes are talking to each other properly over some kind of a Bluetooth channel, some low energy channel. And won't it be just send all where I collect the data and send all to all nodes which are next to me and they send to all nodes next to them and so on? That problem solved. The challenge is that even when we assume some nodes are compromised or crashed, in such an environment, uh, it can happen that such send all is not sufficient at all. Even with a small trick that a farmer can do to a sensor, it may function slightly differently and such a send all may not be sufficient. What we want to make sure that all nodes agree on the set of action or agree on the data that they have collected uh, in a fashion so that the agreement vector of the inputs or whatsoever are exactly the same on all such correctly functioning nodes. And that precisely the operation that is performed by sensor or consensus, where we actually make sure that such an agreement is happening on the data that we are collecting. Even when we have single crash fault, the consensus mechanism can itself be significantly more expensive and challenging as compared to just sending all the information to us. Okay. Another example that I like to talk about is now in livestock. Okay, here we are going to assume that the sensors that are attached to the livestock will be very cheap sensors, so they can only just take the sensor value and send that to the node. They typically we don't expect that to have computation and communication capability to perform consensus uh, agreement of different kinds. So the idea there will be every now and then these drones or these gateways they look at these they talk to these the sensors that are attached to the livestock. And the aim will be they actually may want to track such livestock to see where they are moving or are they going in correct area or is there some particular cow or particular animal is actually facing health issues that should be addressed. And if yes, then where can we find it and can we find out the location for such a cow in a large field? And all those kind of things we may want to perform on it and monitor such information in this particular environment. And their idea could be now again the ranchers here may have advantage to show that the health of their cows or their such animal that they are having is perfect and that there is no issue that they have. While on the other hand, the aggregators or the people who are going to finally going to possibly take a meat from this environment, they want to make sure that the animals that are going into their processing are healthy and perfect. And so there could be advantages for the ranchers to possibly obscure the data and other guys to make sure that they get the perfect and accurate. So note again here we want to make sure that all the sensor information that is collected at the livestock level is collected appropriately by either such in-field gateways or by the mobile nodes such as the drones that are flying over there. And at the same time, what should happen for a meaningful correct processing that these tier two nodes, as we call them, these gateways as well as the drones, they communicate with each other, they perform consensus analytics while helping each other so that we can get the best benefit out of from the chamber. In such a the difference in this environment as compared to the previous example that we saw is that the drones here can be mobile continuously, and given that now we have to deal with how to perform such an agreement, such a process, while still having the mobile nodes. So I think by now, with the three examples that I offered, uh, they should convince you that indeed they are environment where we may want to perform consensus across different nodes, but without relying on they just sending information individually to the other node. How can we solve this problem? And indeed, this is the consensus problem is not a new problem into the environment. Okay, so just to explain the consensus problem bit more pictorially. So typically, what happens in CPS as today with the hubs environment is that all the different nodes that are present into environment, they collect the information and then send that to central aggregator, who decides what action to be taken and possibly then inform those actions back to them. However, we talked about that we may not have such a node. Even if it is present, then uh, it may be ad hoc, available intermittently, may not be always available, and the communication link to such a node could be energy consuming or energy draining for those sensor nodes which are restricted in terms of the energy. On the other hand, what we suggest is that one possibility could be that the nodes themselves perform a local consensus between the users. They have a small code base that's present there that perform exactly these options on the nodes where it is feasible, and then only irregularly when the central node comes in picture that they fetch data from such consensus environment and perform further actions that they may perform, which goes across such different consensus or across such different. As an example, I'm showing here that there are two consensus that are happening in two different environments, but aggregator indeed could be in situation where they collect this information and now propose action based on the two different consensus and two different analytics that are happening in two different environments. Combine that knowledge. It could be very well seen as a federated learning where the two separate learning happen in different environment and a centralized party is collecting this information and performing. However, if you look at this CPS and IoT, it's quite different from the internet, and probably I don't need to tell you, but let me focus on the topic about the topics associated with when we look at this consensus problem or this distributed analytics problem. So in CPS environment, in many of those, we can assume that the nodes are stationary, or that when they talk to each other, they come in a particular situation and then only they talk to each other. Okay. For example, drones may say that they collect information and every hour they're supposed to come to a particular location where they communicate. And given such an environment, it could be very well the scenario that we can assume that these networks are synchronous. That when a message is sent by a node, it is always received by the recipient in a particular time bound, and the time bound will not be exceeded. That's a synchrony. On the other hand, when we build any kind of a distributed protocol over the internet, we inherently assume network to be asynchronous because we cannot guarantee that cannot guarantee that the delay will be bounded by a particular, which is not significantly high. On the other hand, although synchrony makes the CPS setting a bit better, but there is still jamming attacks that are possible. So it's possible for some nodes or some adversary to introduce jammers so that then some communication links do get broken, at least intermittently or for a period. And now we have to deal with such jamming attacks that are possible for that. At the same time, we really don't want to go to the whole way to asynchronous world and solve problems. The next thing is that availability of multicast. We can assume that nodes are stationary. So rather than having unicast where the communication goes from individual node to individual node, there could be possibility to employ multicast and save some energy by using those multicast. While that being true for the CPS and IoT environment, it could be the same case that the network for the CPS and IoT are not fully connected. And again, on the other hand, when we talk about distributed protocols on the internet, we can assume complete connectivity. So the third thing that we can talk about is that for CPS and IoT setting, many of them may not be always connected to energy source. So actually the energy efficiency of such a distributed computation is critical and most important. On the other hand, when we talk about the protocol that are built for the internet, they typically focus on the time, communication, or computation computation effort that are required for the protocol. So they, because these are different measures, they may not directly translate into energy efficiency, and that's a reason we have to revisit the problem by focusing on the energy. And the final thing is that there could be heterogeneous nodes in the CPN's environment. There could be some nodes with significant computing power, while other nodes which are much less. And in that, it's important that we utilize the heterogeneity in a better fashion so that the nodes which are have good communication, computation capabilities are utilized according to them. And it's not that every node is treated. In particular, the distributed protocol that we are curious about, or the fundamental distributed protocol that we are considering, is distributed consensus. We want to make sure that all nodes agree on a same truth or the same information about the data that is present in their environment. And if you look at distributed consensus protocol, because they are built mostly considering the internet scenario, internet communication scenario, what they miss is that they do not address some of the key things that are critical in this environment. So, for example, the existing solution do not address the energy overhead and fairness. They typically focus on just making sure that the time complexity or the communication complexity or competition complexity is small. We want to make sure that the energy overhead is small, but not only at the level of energy overhead of the whole process, but it could be also important that there's a fairness in terms of the energy usage. It should not happen that some nodes drain much more than most of the other nodes in the system, because then we may be losing those nodes. We must want to make sure that adversaries have only limited energy resources rather than allowing him to complete resources. So he can jam the network, but he will be severely limited. He can send fake messages, incorrect messages to sabotage the process, but even that will be limited because the battery power is also limiting adversarial loads that have presented in the environment. That could be interesting thing to utilize and something that is not considered in the existing system. As you already mentioned, we can assume the nodes to be heterogeneous, have partial connectivity, and limited computation energy resources, and that has to come in picture while we perform the actions. And for example, when we are employing any cryptographic protocols for authentication or confidentiality, we have to make sure that we give importance to the limited computation capabilities of it. It can be also the scenario where we have to address the synchronization between the sensor at the low tier node. That's certainly not something which is involved in processing. And before the nodes can perform such an agreement, they have to make sure that they're synchronized in terms of the way they talk to each other and in what way they communicate with each other is certainly an important topic. And most of the protocol doesn't give importance to a K-cast kind of a channel where a node actually may send multicast message to multiple nodes. K-cast means that the number of receivers are equal to K. So taking to those accounts could bring interesting benefits in terms of the energy saving as well as the better guarantee. All right. So we do now with all these things said, we can see that we probably have to rethink the consensus mechanism that we have, and the key focus there could be in the energy efficiency, and we want to build the solution for the CPS environment. And with that, I would like to talk about briefly about our first effort in that environment, what we define as what we call as energy efficient consensus or E2C. So again, I'm trying to portray here the soil nutrition monitoring scenario. So we are assuming that we have different tier 3 nodes which are collecting all this data. And then there are tier 2 nodes which are drones which infrequently visit and collect the information. If we do not assume any consensus, the idea will be, the baseline will be that nodes basically collect the data and send that to the tier 2 node, which come infrequently, and then those nodes take the actions, possibly based on the previous data, and inform those actions to the sensor to behave in a particular manner or collect some information. However, we see that it could be much better in terms of the real-time analytics, efficiency of the communication, and the process in general, that these nodes perform consensus mechanisms with each other in real time, and only infrequently when the tier 2 node is available that there's consensus agreed upon information or agreed decisions are the ones which are informed to the tier 2. And typically, we'll expect that the links between the tier 2 nodes and tier 3 nodes could be extensive. They could be Wi-Fi links or 4G links, while the tier 3 nodes can be easily talking to each other. The key difference I want to say that it's not a completely easy win situation for performing consensus mechanism just on those ground sensors or such environment, because if you see the left hand side scenario could be if I have n nodes which are available, the communication that involved there will be O of n because it's just nodes sending information to one tier 2 node. While on the other hand, when we look at the E2C, here, although communication has been possible in the cheaper channel like Bluetooth channel, but the communication is all to all between the tier 3 nodes, and that's the reason there is inherent quadratic complexity in terms of the number of nodes that associate with it. And the question that we ask that are there scenarios where indeed, when possible, shall we perform the consensus for all? And this is what we did. We actually understand the consensus protocol, build a consensus protocol which can actually take advantage of the K-cast channels which are available into the environment, as well as understand the energy requirement for different communication and cryptography primitives, see which one can perform better or efficient in what scenario. As it turns out, they are very non-trivial decisions that we come across, and I'll be happy to talk about those over a call to several of you. And what we find that indeed there are scenarios where although our process is quadratic as compared to the linear process that happens when we have a centralized aggregator, our process still can perform better as compared to the straw man, as we show with the blue line, in several for different number of nodes. And in fact, with the research study, we are also able to improve the scenarios where we can do much better as compared to the straw man protocol, which is linear. So what we observe is that here we compare them as number of nodes grow, the energy consumed indeed increases. However, it's certainly not something which always bad for the consensus mechanism. There are several regions where consensus mechanism can do much better as compared to the straw. In some applications, the strawman may not be even possible. Let me reiterate that. However, even when it is possible, we may still want to do the consensus first because that's cheaper in terms of the energy, as we show with this particular law. So in terms of the ongoing work now, what we are trying to see is that we're seeing that currently our E2C mechanism, we do not allow jam. So we assume the network to be synchronous. But it's certainly possible in many applications that we have to deal with the jamming where some nodes are basically jamming some other communication between two honest nodes. But at the same time, you want to also put a restriction that adversary just cannot continuously jam the network and create network partition. We are going to assume that adversary is still resource bounded by themselves. Those nodes themselves can only jam it for some duration. They cannot do that continuously. And as long as our consensus mechanism can deal with such short durations or medium-sized durations of jamming sessions, and still make sure that at the end of jamming session they can synchronize together and have a meaningful, consistent state across different all honest nodes, the goal is, and that's certainly the extension that we're working on to make our protocol work against the jamming environment and make sure that it works even again. The key point here is that one way to solve this jamming issue is to assuming asynchronous communication environment that we typically associate with the internet. However, we really do not want to take that step because that can significantly affect the complexity of the protocol involved, as well as it can force us to reduce the resilience that we can tolerate in our environment to the 1/3 rather than the honest majority or 1/2 resilience that we can typically allow into synchronous environment. So to make the resilient point clear, typically in an example that I'm showing here, if I have 5 nodes here, typically the protocol can make sure that it performs agreement in the correct fashion, even when 2 of these 5 nodes are functioning maliciously, are under adversary control, and either destroying the communication that they're saying or sending incorrectly. On the other hand, when we think the network to be asynchronous, then in such 5 nodes, we can only tolerate one bad behavior. So assuming if your network is synchronous, we can indeed tolerate more faults and more faulty nodes than when we are using the system to be asynchronous. All right. Moving on, second scenario that we talk about is when we look at these livestock scenario in general. There, we think that indeed livestock will have sensors, but they are moving, and so are the nodes that are collecting data from the infrastructure. And so in such an environment, as we talked about, we still have adversarial nodes. There could be some nodes that get compromised, may try to collect some information or in provide incorrect information to different nodes. And we are again in the same scenario where we want to make sure that this whole environment, this whole infrastructure, perform actions in a consistent fashion such that all non-compromised nodes continue to function in a manner which is consistent. Okay. In doing that, the key difference with as compared to our previous scenario is that because these are mobile nodes, now we have to make sure that our distributed protocol can deal with the mobile. In that direction, the two key approaches that we follow is dealing with mobility or dynamic nature of the graph and the consensus mechanism. And such CCS nodes are continuously in the move. We want to make sure that even when they are moved, we can achieve the consensus in such a dynamic setting. The challenge here is this is not a well-studied problem, and although there are some theoretical models which are present, we haven't yet linked those to the real way how drones move into different or how such mobile nodes move in different environments. So, what study that we are undertaking as a part of our project is to understand what kind of communication and movement that these different nodes perform. Is there a pattern that's meaningful? And for those patterns, then can we make sure that we still can perform meaningful agreement across these different nodes? And that will involve understanding the necessary communication bounds and conditions that are required in such environment, and then building protocols to deal with that. And we are really excited to work, and we are continuously working on this. One interesting problem that occurs in such environment is that in many such settings, we may not want perfect consent. It is sufficient to have approximate consent. What I mean by that is that even when honest guys or non-compromised nodes they agree on something, they may not be agreeing on the exact same value. They may be agreeing on the values which are next close to each other. And the examples for that could be, let's say we want to look at the location of a livestock. And it's not important that we pin down that to a very minute scale at every degree or something. It is sufficient as long as all nodes agree on that location to a really good extent. It's not perfect. Okay. Or it could be altitude and alignment across different zone environments, where also perfection is not necessary as long as the information that is agreed upon in same ballpark, that could be sufficient. Okay. Another example could be that different drones see some particular location of a particular device on the ground, and they want to make sure whether it is a blue or red, whether it is the device that is associated with the drone environment or it's an adversarial device. And there also they can actually look at this device from different angles and may have different value. And as long as they all agree on leaving away the perfect example, as long as they all agree on that with 60% probability, 59% probability is red versus 40% probability is blue, as long as their agreement values are close to each other, that could be sufficient. So there are indeed many scenarios where we do not want perfect consensus because that could be expensive, and instead it could be sufficient to approximate consensus. So the key property in approximate consensus is that the value agreed upon by two correct non-bicentennial nodes at the end of the algorithm do not differ by a predefined value. There is a bound that defined and it remains in that bound. And so it could be sufficient in the environment, and once we have dynamic nature and approximate consensus, that brings us a very interesting problem and challenge to deal with by itself. And if we add analytics on top of that, so that we take these values, analyze those based on the approximate values that are agreed upon, could be interesting challenge and task to be done that we are working. The third topic that I want to mention here in terms of an interesting challenge is regarding confidentiality. So in many environments, we can assume, especially in the adversarial environment for sure, that some of these nodes can get captured and compromised. if in our current environment, we're talking about indeed these nodes talking to each other and sending each other data. Now you see, even compromise of one node may result into the data from all the systems to be now available to them. So what we want to make sure that capture devices can obviously can obviously uh, can get compromised and reverse engineered by the adversary. But while we do that, it should not hamper the confidentiality of the system. So we want to make sure that when the nodes get compromised, they only get information, but such that as long as adversary cannot compromise a large number of such nodes, they cannot figure out this precise information. The way we typically try to achieve that is to be employ mechanisms such as secret sharing, where nodes do not send each other exact value that they capture or exact data that they got, but they actually secret share them and send them to each other, and such that eventually, when they are when some kind of action has to happen or some kind of agreement that will happen, only at that time the reconstruction of such shares can happen, and the data will be available on those individuals. And as long as adversary cannot compromise the threshold number of nodes, the confidentiality remains intact. You can see the shares, but in knowing individual share doesn't provide any information about the actual data that is found. And this is the entirely new domain which is not studied for drones at all. It seems like a very interesting problem to deal with. That how can we deal with the confidentiality? In fact, if you see this problem at core, is closely related to a problem in distributed and cryptography, distributed systems and cryptography field called multi-party computation problem, or MPC problem. So what MPC problem says is that they're n parties and they are each have a private input, and they want to perform some kind of function on that, some kind of analytical function on that, and output should be the output of this analytical function. However, so far so good. What we want to indeed make sure the first good is that the output is correct. Okay, which is correct, that indeed for given input that output is correct. What typically the key property that MPC asks for is the privacy or confidentiality property, which says that an adversary should not be able to determine anything beyond the output if that's available to them. So he can obviously look at the output if that output is sent to the all drones and the drone gets compromised. However, other than the output, they should not be able to obtain any information for the input that is coming from the input. So this kind of guarantee, and if the output is not present onto the drone nodes, then we are doing even much better. The third property is termination, where we want to indeed make sure that such a process terminates. I mean, having correctness and privacy, if there's no termination, is not meaningful for service. Again, as you already mentioned, this is threshold bounded kind of a scenario. So we'll assume that adversary is T-bounded. Out of these n parties or n drones that are performing communication, some subset of those could be compromised, but that could be well-defined subset. For such a system to function correctly, we will have to assume that the channels that are used for communication are not only authenticate but also private, so that an adversary with the antenna should not be able to just capture the share that are sent by the node, because otherwise they can always reconstruct and obtain data just by listening to the channel and not even compromising. Again, this is certainly something that we're excited and working on, and we look forward to seeing more about it. When we look at this particular, the current solution that are available for the MPD problem, none of the existing solutions address the network modalities that are typically associated with the CPS and IoT. And indeed, that brings an interesting challenge by itself to build MPC protocol, build multi-party computation protocol, which can work for the CPS and IoT setting, and this is certainly something that we are focusing on. All right, so with that, I'm coming to the end of my presentation here. I like to emphasize the point that these are the few example scenarios we thought where we have to deal with the distributed protocols and multi-party computation protocols to deal with such a case. But there could be indeed many other scenarios where CPS and IoT get used. And indeed, I look forward to hear from you what kind of interesting scenarios that you can think of. And please reach out to me. I'll be very happy to hear about your thoughts in terms of the direction we are taking, as well as in general, if you see some challenges that we may face in this environment, and also the applications beyond what we thought already, where we could employ that. And we look forward to hear to you and possibly start with collaboration. All right. So with that, I'm going to thank you. You can find more about kind of things we are dealing with the distributed consensus mechanism in the CPS setting as well as for blockchains in general from our webpage. And you can also reach out to me at Aniket at Purdue, and I look forward to you.
Thanks, Aniket. Thanks for that talk. I really appreciate you coming in and speaking to our session this afternoon. At this time, if you have questions, please feel free to enter them in either the Slack channel, or we're a small enough group that we could use the local chat. Just make sure that we have a way to know that you have a question. And we have another 10 or 15 minutes. We can talk for a little bit about the presentation. I see Aniket's joined us live and in person, so he can address your questions directly. So no questions? I haven't seen anything pop up yet. Okay, Aniket, do you have any other additions you'd like to add to the recorded presentation? Any comments or thoughts? And then if not, we'll give everybody a little bit of a break, and we'll meet back in a few minutes.
Sure. I'll just add very briefly that this is a topic that we are spending significant times, and we are looking for interesting applications in CPS settings. We looked at only with the ARL project, we looked from the military perspective, and also we are looking into the farm and agriculture perspective. But IoTs are pervasive all throughout different environments, and if there are scenarios where we can employ distributed computing settings, this is certainly something we wish to spend a lot of time. And you can reach me out later sometime once you have gathered some more thoughts, or if you looked at the presentation. I have also attached my slides on the Slack channel, and I'll be more than happy to send you and answer you if you have any questions via email.
Okay, thank you.